the last lecture, we discussed series and parallel combination of resistances and also series, parallel and mixed combinations of cells. We defined the EMF of a cell and we also defined the potential difference across the terminals of a cell when current is flowing. One important thing that we learned was that when the cells are put in parallel, the voltage supplied to the circuit does not increase, but their capacity increases, that is the time for which they can supply current to the circuit increases. As if we have got when we put cells in parallel, it is as if we have got a much larger cell, single larger cell, and this contains much greater material than a single cell, and therefore, its capacity increases. Now, if we have a complicated circuit, say like this or like this or like this, I mean if we have a complicated circuit, how do we find the currents in the various arms or the potential differences across various resistances or the terminals of the battery or resistances for that matter? How do we do that? This is done with the help of Kirchhoff's circuital laws or simply Kirchhoff's laws. Before we look at these laws, let us look at a few definitions. Let us take this circuit. At the point A, the current gets divided, part of it goes beyond A to B and part of it goes to D. At B again the same thing happens, part of the current coming to B goes to C and part goes further. A point at which division of current takes place, some currents come, some currents go, that is called a node or a junction. Say for example, point C, the current is coming from this side, also coming from this side, but going on to this side. This C is called a junction or a node. On the other hand, a closed loop, a closed part is called a loop, and the loop can be traversed either in the anti-clockwise direction or in the clockwise direction. So, we shall make use of these loops and junctions or nodes to state the Kirchhoff's laws. Note that since charge cannot accumulate anywhere, whatever charge comes to this node from all the sides must go out. If the charge comes from this and from this, all of this must go out. That means, the charge cannot remain at the point C. That means, this current, if it is coming to this C and this current which is coming to C, their sum must be equal to the current that is leaving C. This is actually the first law of Kirchhoff. It says that if there are n currents at a node, then the sum of these n currents must be equal to 0. I 1 plus I 2 plus I 3 plus I 4 must be equal to 0. To understand this, take this example. At this node, the currents coming to are I 1, I 3 and I 5, and the currents leaving are I 2 and I 4. And if I give positive sign to the currents coming and negative sign to the currents leaving, then I have I 1 plus I 3 plus I 5 plus minus I 2 minus I 4, or I 1 plus I 3 plus I 5 is equal to I 2 plus I 4. That is, the sum of the currents leaving is equal to the sum of the currents arriving at that node. This is first law of Kirchhoff. Second law of Kirchhoff is called voltage law, and it deals with voltages. And what does it say? It says that the algebraic sum of potential or voltage drops in a closed loop. Remember the closed loop? This is a closed loop. In a closed loop must be 0 if we traverse the loop consistently in a clockwise or counterclockwise direction. So, when we are dealing with loop, we have to choose. We either go clockwise or we go anticlockwise, and this has to be done consistently. If you have two loops, then in one you can go clockwise, in the other you can go anticlockwise, but in one loop you must go all the way, either clockwise or anticlockwise. And if we do that, then V 1 plus V 2 plus V 3 plus V 4, they all must add up to 0. Take this example for this loop, and we are going to traverse this loop in anticlockwise direction. So, you see in this the current I 1 is like this. So, it is in the same direction as the loop. Therefore, the potential drop across R1 is I1 R1. Then this current I2 is in the direction opposite to the counterclockwise direction, and therefore, the potential drop across R2 must be negative. So, I1 R1 plus algebraic sum we have to take. So, minus I2 R2, that is equal to 0, or I1 R1 is equal to I2 R2. That is a statement, in fact, that they have a common potential difference. What happens when the sources of voltage are present? In this loop, there was no voltage present, no battery present. Here we have got batteries. So, what do? The rule remains the same. We must consistently go either clockwise or anticlockwise. Now, if in doing so, say we choose anticlockwise direction, if we come across the negative terminal of the battery first, then the voltage of that battery is taken as negative, and if we come across the positive terminal first, as here, then its voltage is taken as positive. So, let us apply this to this loop. Once again, we are traversing it anticlockwise, and here the current is going up. So, when we take the loop anticlockwise, we meet it in the opposite direction. So, the potential difference across this must be negative. So, minus I1 R1, and we meet the positive of this battery. So, plus V1, and we meet the negative of this battery as we are going anticlockwise. So, minus V2, and we meet the current in the same direction. So, it is I2 R2, and this all this must be added up to equal to 0, which means V1 minus V2 is I1 R1 minus I2 R2. For this source, remember the following rule, which I have stated earlier also, but let me repeat this, because this is very important. If during your traversing either clockwise or anticlockwise, you meet the positive terminal first, then its voltage is taken as positive. If you meet the negative terminal first, then its voltage is taken as negative. You see, here we had the counterclockwise, here we have the clockwise, and you can do the same exercise again, and you will get the same result. V1 minus V2 is I1 R1 minus I2 R2. So, it does not matter. In a given loop, you can go clockwise or anticlockwise, it does not matter, as long as you are consistent. Now, let us take two loops. We have added another loop, and just to explain things, and this loop we traverse anticlockwise, and this we traverse clockwise. I told you that in one loop you must be consistent, but if you have two loops, you can have in one loop you can traverse anticlockwise, in the next one you can traverse clockwise, it does not matter. You can have here anticlockwise, here you can have clockwise, you can have both anticlockwise, you can have both clockwise, it does not matter, as long as you are consistent. So, what happens now? Say take this loop using Kirchhoff's voltage law for the second loop, all right. We take this loop, and this is clockwise, and as we go clockwise, we meet the negative terminal of battery V2. So, minus V2, I1 is in the same direction as the clockwise direction of the loop. So, I2 R2 is positive. We meet this battery, the negative of that. So, minus V3, and meet the negative current. Current is going this way, but we are traversing the loop in the opposite direction. So, minus I3 R3. So, that is how we do in different loops. Now, you take this example. Consider the circuit shown, values are given. We have to find the current in the arm PA, in this arm, and the voltage of the battery. To find the voltage of the battery, we need the current, this current, as well as the equivalent resistance. I mean, you without going through the Kirchhoff's laws, you just can find the resistance. These are parallel resistances, find the resistance, and therefore, you can find the voltage if you know the current. So, you can do that, but let us apply Kirchhoff's laws. This example is almost trivial. At junction C, this current is coming this way, this is coming this way. So, the current is 0.15 plus 0.05, that is 2, and therefore, the current going must also be 0.2. So, the current going at C to arm CD is 0.2. Similarly, you can find the other currents, and then you can, the effective resistance is simply the resistance in parallel, 1 by 60 plus 1 by 80 plus 1 by 240, and this R effective therefore, is 30 ohms, and we can, the total resistance here was 2.2, and here the 0.2 coming from this is added up. So, this becomes 0.4. So, the total current is 0.4, the effective resistance is 30 ohms, therefore, I times R is 12. So, you get 12 volts. Again consider this circuit. So, we now, as I said, we can use our discretion. In this case, I have taken all the 3 loops in the anticlockwise direction. So, the data is given, this is 20 ohms, this is 5 ohms, this is I 4, I 3, I 2, I 1 and like that, and this is 10 ohms, this is 5 volts, the data is given. So, we shall use the Kirchhoff's laws, you see how many currents are there, 1, I1, I2, I3, I4. So, we have to suppose determine all the 4 currents. Then we need at least 4 equations. 3 equations we will get from the loop, one loop, one loop, one loop. One loop is this, another loop is this, and another loop is this. So, we chosen these 3 loops, and one will use junction C. So, we shall have 4 equations, we will solve them simultaneously and get the result. So, these are the equations 5 minus 10 I. Take this loop for example, this loop is anticlockwise. So, we meet the positive first. So, therefore, 5 is positive and the current is going this way, but we are traversing the loop this way, therefore, minus 10 I, that is equal to 0. In a similar way, you can write the equation for this loop, write the equation for this loop. You can verify that these are the equations for 3 loops 1, 2, 3. And at junction C, what is happening? This current I 2 is coming and I 3 and I 4 are leaving. Therefore, I 2 must be equal to I 3 plus I 4, that is I 2 minus I 3 minus I 4 must be equal to 0. You solve these equations simultaneously and you get this result. So, the application of Kirchhoff's laws makes things quite simple for us, however complicated the circuit may be. Applying the voltage law to the circuit shown, we can write, you see, just for practice, we are doing this in the clockwise direction. When do you do that? We meet plus sign of this, therefore, 25 and then the current is going this way. So, we meet the current in the opposite direction, we are going this way, the current is going this way. So, minus 100 I and then we meet this battery at its negative terminal. So, therefore, minus 15 and this minus 150 I, because the current is going this way, we are going this way. So, we can solve this and get the current. You see, it would be difficult otherwise, because we have 2 cells now and difficult to find the current, but use of Kirchhoff's laws makes it very simple. Now, we consider these 2 loops and now again there are 2 batteries, 12 volts here and 6 volt here. So, we do not know which way the current will flow. So, this is also important, we do not know, but let us arbitrarily put the directions of the currents. So, at junction J, this current I 1 is coming, I 2 is going, I 3 is also coming. So, I 1 plus I 3 is equal to I 2. These 2 add up and give you I 2 at junction J. For the upper loop is anticlockwise and therefore, we meet this V at its positive terminal, the potential at its positive terminal. Therefore, it will be 6 and this, since we are going this way, this we meet in the opposite direction. So, minus 24 I 2, this also we meet in the opposite direction. This is 36 I 1 and I 1 R 1, R is 36, therefore, 36 I 1 and this is 24 times I 2. So, if you give proper signs, then you will get 36 I 1 plus 24 I 2 equal to 6. And similarly, for the lower loop, again we are traversing this now in the clockwise direction. When we do that, then this potential difference will be negative, because we are going in this direction and the current is going in this direction. So, it will be 24 times I 2, 24 times I 2 and this current we meet in the same direction as the loop. Therefore, 12 times I 3 and we meet the battery at its positive terminal, therefore, 12 equal to 12. So, you get these 3 equations and you can solve them and get solve them simultaneously, get the currents. What is important is, you see, we arbitrarily said I 1 will be on this side, I 2 will be on this side, I 3 will be on this side, we put them arbitrarily. But when we do that, we find that although I 1 is in this direction, I 1 is actually negative, that means I 1 must be in this direction. So, what it means is that since I put I 1 in that direction and it turns out that I 1 must be I 1 is negative, that means I must change the direction. So, by using these laws Kirchhoff's laws, I can also find the direction of the currents if I do not know initially. This implies that the direction of I1 is opposite to that shown in the circuit. So, even if we mark the direction of currents arbitrarily as we did, the solution of the equation will allow you to get the right directions. So, the Kirchhoff's laws, if you have given data, you can find whatever you want to find, resistances, voltages, currents and so on. The important circuit is Wheatstone bridge. This is the basis of your experiments with meter bridge and potentiometer and so on. What we do here is a circuit which has 4 resistances R1, R2, R3, R4. One is can be here, but not in this case, we have a galvanometer which also has a resistance anyway. So, what we do is we find conditions so that there is no current through this arm B D, and if this is no current, then we will find that R1 by R2 is equal to R3 by R4. That is, if you know any 3 of these resistances, you know the 4th. Now, to do that, we divide this into 2 loops. We apply the loops in the anticlockwise direction, write down the equations, and then we will solve them simultaneously. And these are the equations for the 2 loops, this loop and this loop, under the condition that there is no current through this. So, minus I1 R this loop, in this loop I1 R1 plus I2 R3 is equal to 0, and in this loop I1 R2, this is in this direction. So, I2 R4 is equal to minus I1 R2 is equal to 0. So, we can solve them, and you can get take this on this side, divide one by the other, and you will get R1 by R2 is equal to R3 by R4. This is known as the balanced condition for the balance of the Wheatstone bridge. And if we replace the galvanometer by a resistance, then we have all this complicated circuit. Again, we can take 2 loops. Suppose we have to find all the currents I2, I1, I2, I3, I4, I5. So, we will need 5 equations, and what we can do is we can have one loop and one loop like this, 3 loops and 2 junctions we can use, and we can get 5 equations, solve them, and you can get the result. These are the equations for loop ABD, for loop ADCEF, and ABCEF. So, these are the 3 loops we have used, and then junction B and junction D, junction B and junction D. That is, here this current is coming, this is going at this place, this is going, this one is coming, this one is coming. So, we used these junctions and we solve them simultaneously, very simple for you, and you can find the currents in various branches. And if you are given resistances, you can find the effective resistance and you can get the voltage. You see, these 2 are in series and parallel to this, and or you can, and then whatever you find is in series with this and parallel to this. So, you can find the effective resistance and get the voltage. This complicated looking circuit is nothing but actually a Wheatstone bridge. All the resistance are there, they are all equal in this case, and the bridge is balanced because all the resistance are equal, and therefore, the effective resistance you can find no problem. Sometimes you will get a circuit like this, again looks complicated, but if you think for a moment, you will see that this is nothing but a Wheatstone bridge. You have this 10 ohm here, and this 20 ohm here, and this 20 ohm here, and this 40 ohm here, and 80 ohm here. So, we will have these, and these 2 are of course in series with the battery, and this is balanced. 10 by 20 is the same as 40 by 80. So, if they are balanced, therefore, there is no current through this circuit. Through this resistance there is no current, and therefore, you can find the effective resistance, and you can find the effective resistance of this is how much? 20 ohms, and this add to this 30 ohms, and the total resistance is 50 ohms. The important thing to notice is that this is nothing but a Wheatstone bridge, and it is a balanced Wheatstone bridge. So, you can ignore this 20 ohms. Similarly, this circuit, this is a very complicated circuit. Again, you can divide this into loops, 1 loop, 2 loop, 3 loops, and you can also get 3 nodes, and equation for these nodes are here. So, all these equations are there, and you can solve them simultaneously, there is no problem. It is a little algebra, you can do that, but just algebra, nothing very difficult. All that you have to do is to sit back and think what to do, but you can solve these equations, there is no problem. So, in this lecture we have concentrated on Kirchhoff's laws. As I said, Kirchhoff's laws are very useful for what? For finding out the currents in various branches of a very complicated circuit, voltages in various branches of complicated circuits, resistances, if the adequate data is given. What you do is you divide the circuit into loops, write the equation for the loops, remembering that each loop has to be traversed either clockwise or anticlockwise. And if in traversing the loop you get the negative terminal of the battery, you encounter negative terminal of the battery, then the voltage is negative. If you encounter the positive terminal of the battery, then the voltage gets a positive sign. If you remember this, then the application of Kirchhoff's laws is not difficult. All that you need to know is a little algebra, because simultaneous equations 5 or 6 or 4 you have to solve. So, here we have shown you the various examples how one can do that. In the next lecture, we shall take the magnetic effects of currents.